Welcome to Spring LIB.
We're going to have a block that's oscillating on a spring, and that spring has a spring constant of 100 newtons per meter, and it's got a mass of 4 kilograms. Then we're actually going to end up putting another block on top of it, right? And that guy has a mass of 6 kilograms, right? And we're asked to find what the new amplitude is. So it actually tells us that the original amplitude was 2 meters. And we want to know what the new amplitude is. I'll call it A2. Okay? There's a lot going on in this problem. So we're actually going to start. This is a conservation of momentum problem. So we're going to have the mass oscillating back and forth with some velocity. And then it's going to collide with the second mass. So we need to figure out what that velocity is. Right? But that's the maximum velocity of the system, right? We know that A1 is 2, so we just need to know what omega 1 is, but that's the square root of K over M1, right? And K is 100, M's 4, so that ends up being 5 hertz. So V1 actually ends up being 10 meters per second. Okay? So now we can use our conservation of momentum that says that M1 V1 plus M2 V2, and they stick together so we can combine their masses, right? And the original guy that's getting dropped has no velocity. So we have 4 times 10 plus 0 is 4 plus 6 V prime. Right, and so if you solve this, you actually find that the new speed is 4 meters per second. Not surprising, it lost energy, lost some speed in that collision. So it asks about the new amplitude, right? And the easiest way for me to see this is that it's still going to be equal to A omega, right? Because that's still the maximum speed, but this is the new frequency, and the new frequency is K over their combined masses, right? So this is 100 over 10. So this is about 3.16 hertz. So the new amplitude is going to be 4 over 3.16. Right? So you can go plug that in your calculator, and I get about 1.26 meters. So that's the new amplitude. Right? So the problem wants more than that. It wants to know how the period has changed, right? And by how much. And we can actually see here that the frequency, right, got 3.16 divided by 5. It got 0.63 smaller, right? But the period goes like 1 over that frequency. So we're looking at like 1 over 0.63. And you get about 1.6 times longer, right? So you have a longer period just because it has more mass. Okay? So other thing it wants to know is how much energy we've lost. Okay, so I'm going to make some room here. Right. And the energy we've lost has to do with that speed we calculated. Right? So before we had 1/2 KA squared, right? The original one, right? So that's a half times 200 times 100 times 2 squared. And if you do that, you end up with 200 joules. And now in the new case, we have 1/2 K times this new amplitude, 1/2 times 100. We said that was 1.26 squared. When I did that, I had 120. 50 times 1.26. I got 79 joules. So it lost about 121 joules. And the question is, where did this go? So it lost energy, so this is an inelastic collision, and typically that gets turned off as heat, or you could think of it as the internal energy of the blocks, right? The molecules inside there moving faster. There you go.